Hi, folks. Welcome to the session. It's Friday morning. It's bright and early. Thank you very much for being here. If you ask me, it's the best day to be here because there's no distractions, no booth, nothing. You get to go focus in on sessions. So I'm very excited to have you guys here. We have some great speakers with us today from both Oracle as well as MongoDB who will be joining me on stage. And we will collectively cover the best practices in terms of running any workloads on Azure Disks. And so we have a ton of great content, some wonderful live demos. So let's keep all our fingers crossed that the internet is going to support us. But let's get started. So if you look at users of Azure, there are a ton of different enterprises and customers looking to migrate their applications from on-premises to the cloud. And there's a ton of different triggers around this. It could be the end of a license. It could be the need to sort of refresh your infrastructure or to overall reduce cost. Whatever may be your migration trigger, there are sort of two paths that we see people think about. One is, should I lift and shift my application as is to the cloud? And second, should I rebuild and refactor my application to now take advantage of cloud-native capabilities, right? This is a common question and something that everyone needs to think about. Now, lift and shift is a very common way to go and a great way to get exposure to the cloud and start your move to the cloud. And so lift and shift, some common questions that we get are, how do I lift and shift the application and make it work as is? How do I not have to rewrite a bunch of things just to get started with my applications? Next is, how do I actually get the right workload performance by potentially making small tweaks either in the platform or the application and actually getting the best performance either equal to or better than what I see on premises? And last but not least, we also get questions around, hey, we know you have guidance around SQL Server, but do you also have guidance around other workloads like open source databases and other capabilities, right? So we're here to answer these three questions today as part of the different workloads that we will cover. Now, some common workload types that we see as we talk to different customers who run on Azure are relational databases. That is obviously extremely common. We also see NoSQL databases are very, very common, as well as big data solutions as a way for people to, again, lift and shift before they move to hosted big data managed solutions in the cloud. Now, some popular applications in these three categories include things like SQL Server, Oracle DB. With NoSQL, you think about applications like MongoDB and Cassandra DB. And then with big data, you're really thinking about things like Hadoop and Elasticsearch, right? So these are some great examples and common workloads that we see customers run as part of their deployments on Azure. Now, when we talk about performance, let's set a bit of a baseline. What are we talking about when we say performance? So the first thing is throughput. So what is throughput? How much data can my application actually process every time I'm actually sending requests to this application, right? So that is what is throughput. Next is how many requests can my applications actually process in a specific period of time? And that is called IOPS. And now IOPS and throughput are actually extremely related to each other. Now, the number of IOs that I can send to my application into the size of each IO really determines the overall throughput that I can pass to my application. And last but not least, the golden question, which is how long does my user need to wait every time they send a request for them to actually receive the response that they need, which is latency. Now, your application may be sensitive to one or more of these parameters. So we really need to think about how do we tweak these parameters. So maybe you could maximize throughput because you're trying to do ingest, or maybe you're trying to maximize or minimize latency as much as possible because you have a workload that's extremely latency sensitive or your customers are extremely latency sensitive. So now that we've learned these three simple terms, let's think a little bit about the different offerings that we have as part of Azure Disks and how these relate. Now, if you have an application that's not I/O sensitive, you're really looking at the standard tiers. You could look at standard HDD, which is magnetic drives, standard SSD, which is for applications that have low IOPS but require low consistent latency. But if you have an I/O sensitive or latency sensitive workload, you have to really look at the right side of the spectrum, which is really around premium SSD or ultra disk. Now, premium SSD is your default for applications where you need very high IOPS and low consistent latency, and that really maps to capabilities like databases. But when you need something like sub-millisecond latency, you would want to think about putting those workloads on an ultra disk, because that is really going to give you very, very high IOPS on a single disk, as well as extremely low latency. So these are the four types that we have in terms of disks, but then we also have sizes in between that. So once you sort of realize the I/O characteristics of your application, you've decided which disk type to go with, you're then looking at the size that will give you the exact parameters that you need. An example of this would be a P30 disk, which is a 1 terabyte disk, which gives you around 5,000 IOPS. So if that's the range you're looking for, that's the size that you would want to start with. Now, some simple tips and tricks after you've sort of picked your database, your disk types are the following. First, we have this extremely unique capability on Azure, which is called as the host cache. And what the host cache does is it exposes some of the SSD that is inside the Azure host to the application in the form of a read cache. And what that does is it increases the IOPS of your application and reduces the latency of your application significantly. And so if you have a read-heavy workload, ensure that you always have the host cache on. And the way that you do this is super simple. When you mount the disk in the portal to the virtual machine, you have a setting there which is called read-only cache. So you can enable that, and that's a very easy fix. Next up, isolate files based on your application characteristics. And this is something that a number of people have been doing on premises as well, and this is something that you take with you to the cloud, which is if you have a database, for example, you will have data files which require low consistent reads, put them on premium with your host cache on. You will then potentially, if you need sub-millisecond writes on your log, then put them on an ultra disk, but isolate those from a disk standpoint, put them on different disks, as well as your temp DB. What do you actually need it for? Is it just for sorts and order bys that you're not going to persist? Then consider using local SSD, because that's going to give you great performance, but not actually you don't actually have to put it on a separate managed disk. Last but not least, the VM type is super important. If you choose a VM that does not have the throughput and the IOPS that is actually required to maximize the underlying storage, you will not see the application performance that you're expecting. So you could keep adding disks, but if the VM is going to actually be your constraint, then you will actually not see that performance show up as part of your application. There are memory optimized VMs, storage optimized VMs that could be great for this. And every time you pick a VM, check the throughput and check the IOPS that the VM is capable of to ensure that you're maximizing the underlying storage. Now that we've sort of learned some of the platform capabilities, the thing to also think about is every application itself is different. There are some that are inherently have low queue depth or queue depth of 1, right? Or where you're not really seeing much parallelization. Or you could have a random access workload. Whatever your workload pattern is, ensure that you're setting up your platform to actually support the characteristics of the workload. And this is what we're really going to be talking about for the rest of the session as we take different workloads and look through different characteristics. So let's start with relational databases. With relational databases, I'm going to start with SQL Server. Now, with SQL Server, the SQL team has really taken some of the key aspects of what we just talked about in terms of best practices and factor that into their overall best practices documentation. And I'll share a quick link to that in the next slide. Now, from a VM standpoint, they really recommend using the ES series or the DS series as your sort of general purpose starting point for maximizing the SQL servers on your infrastructure. They take care of the read-only cache. They recommend that you use UltraDisk if you want some millisecond latency. But what they've done on top of all this recommendation, they have actually put all of this into a resource provider that will serve up these recommendations as part of your SQL Server creation process. And we're going to take a quick look at this as part of a demo. So let me switch to my demo machine here. OK, so here I have now initiated the create process for a SQL Server. And this is just a simple create process from the marketplace. What I've done is I've pre-filled some of the information around the region, subscription, and all of that, as well as I have chosen a VM size. What I notice immediately is that there is now a tab here called SQL Server Settings. So I go into SQL Server Settings, and then I go down here, and then I can see a number of recommendations around SQL Server. But what I notice here is that they have storage optimization choices. I go to Change Configuration. And now this pops open a configuration tab that allows me to choose what is going on with my disks. Now, if I have a transaction-heavy workload, I now can go down here, and I can choose that, OK, I'm going to put my data drives on F, and I'm going to use a premium SSD. I can also choose the number of disks I want if I'm expecting to create a stripe set. What I can also do now is, as we talked earlier, if my log is going to require extremely sub-millisecond latency writes, what I'm going to choose to do is put that on a separate drive. I could choose to put it on the same drive, but I choose to put a separate drive, which is G. And here, what I'm going to do is I'm actually going to choose UltraDisk. Now, we haven't updated this. UltraDisk is actually in general availability, but we'll go do that right after we leave this session. But once that is done, what I can do is I can say, hey, my log disk actually needs 10,000 IOPS. I want 1,000 throughput. And that's it. I set it up. I decide that I'm going to separate my files into different disks. And then last but not least, for TempDB, I decided that I actually just want to use local SSD, because that's the best experience for me, and that's picking the D drive. So that's it. And just like that, I am able to apply a lot of those best practices that we just talked about as part of my creation flow, right? So and now if I hit review and create, this will create the VM for me. Now, next up, there's a company called GigaOM who runs performance benchmarks. And what they did is they ran a performance benchmark for SQL Server on different cloud platforms. They looked at Azure and AWS. And what they really see is that Azure is the platform on which they actually saw the best performance for running SQL Server. So not only did they observe that it ran much faster, so 1.5x faster than on AWS, they also noticed that it is significantly cheaper to run SQL Server on Azure than on AWS. This is an independent study, and these are sort of the benchmarks that they have. This should get published for you to look at in the coming weeks. With that, we are going to invite Sean on stage to come talk a little bit about Oracle and Oracle DB.
Hey. Thank you, Vaibhava.
Take it away.
Good morning, everyone. As Vaibhava just mentioned, I'm a director of product management with Oracle's database team, and I have a quick cameo to present, and I have 5 to 7 minutes, so I'm going to go as quick as I can. The first thing I want to talk about is, well, the whole conversation is going to be based on ASM, Automatic Storage Management. I guess a show of hands, who is using Oracle databases today? Oh, a few of you, good. Who is using ASM today? Wow, that's Excellent. Okay, so good one. So for those of you who may not be aware, ASM is Oracle's automatic storage management, and it's something that came out with Windows, with Oracle's database version 10 back in 2003. Windows 98 was the desktop, right? So that's how long it's been out. Prior to ASM coming out, if you cast your mind back to the early days of performance tuning a relational database, there was this model, it was almost alchemy, where a DBA or a sysadmin would figure out what tables and what pieces of an application required what type of throughput, and they would put some of their data on disk 1 or volume 1, and their indexes for this application on volume 2, and their system table spaces on another disk. And they would play this game, which worked really well to isolate and to speed throughput up for them in particular situations. But often they would introduce a new application, and then they would have to put the application tables for the second application, where the indexes for application 2 was, and it became a nightmare. Same case when we did TPCC benchmarks, it would take us weeks to configure the storage to work optimally. So one day, someone came up with the bright idea of saying, well, what if we just put all our data into the same set of disks, stripe and mirror everything across a bunch of JBODs, if you wish, just a bunch of old disks, and see what the performance would be. So they came up with this model, and it just made things run much more easier from a manageability standpoint, because you didn't have to figure out what workloads were doing what updates, inserts, writes, etc. And lo and behold, it actually ran much, much faster than this old way of doing things. So we came out with this model called stripe and mirror everything. There's plenty of white papers written back in the day if you want to look back to it. But ASM is an evolution of that, where we're implementing that for you. So we stripe and mirror everything across the disks. It could be JBODs. You could be running on top of JBODs. You could be running on top of RAID. It could be RAID 5 if you want to run ASM on top of that. And that's what we're talking about now. So ASM provides a simplified volume manager. That's the easiest way to think about it. And Vaibhava and myself had quite a few conversations about what's that secret knob that you can twist to make ASM run faster. What's a special tuning parameter you can put in there to make it run faster or to affect the throughput? And the reality is ASM is not intended to do that. It's intended to be optimized for you out of the box, okay? So with that being said, it's an integrated custom volume manager. It can provide a shared file system for you on top of that. It stripes and mirrors everything across the disks to provide redundancy and performance by distributing those IOs across all the disks. It automatically rebalances. Now, this is one of the big things that ASM added that the same model wasn't able to do, which is you can remove disks from the stripe set, or you can add disks, and ASM will rebalance that workload dynamically and automatically across those disks for you without any interruption. Now, one thing to keep in mind, because ASM is a volume manager, it provides a metadata cache, a metadata dictionary, if you wish, to how your physical storage is based on disk. So the database starts up, and the database looks at this ASM volume manager and then has its directory structure to where these blocks and segments are stored on disk. So this memory structure is an Oracle instance that resides on a server, and that instance, if we're going to create a memory structure, we'll leverage an Oracle instance, is what we use to access that system. Keep in mind, any I/O operations going through that instance, any activities going against that instance does not include I/O. So it's a volume manager, right? It simply tells you the metadata mapping and where everything is located on disk. It doesn't actually it's not being asked or requested anytime you want to do an I/O. So in theory, you could have an ASM instance that's running for over a week without actually ever being accessed. It gets access to start up the database. It gets access to modify the physical structures on disk and other tasks such as that. But actual I/O operations do not get impacted by it. Another thing to keep in mind, we actually provide a shared storage model with ASM. So if you're running a cluster, if you're running a cluster of any kind, ASM will provide a mapping across that shared storage as well. And back in 12C, when that first came out, we introduced the ability to set up what we call ADVM, ASM Dynamic Volume Manager, so you can mount a regular file system on there, or you can use Oracle's ACFS, ASM clustered file system, which is a POSIX-compliant file system for storing non-relational information if you want to put data such as that there. One final thing, ASM, along with ACFS, is what we call our Oracle storage stack. So that was my quick intro on it. Some best practices, the instance configuration. First of all, that instance that I talked about, it occupies only 1 gigabyte of RAM, and we use that for just providing a standard pattern for deploying these databases, and we found that seems to be the sweet spot even in these shared clusters. Now, one thing to keep in mind, it is an instance. You can log into it, you can set parameters, you can query SQL views, etc. But there's a parameter called processes, right, in a database, if you're familiar with an Oracle database. For an ASM database, when you go and fire that instance up, if you're supporting less than 10 databases, the math is that you would multiply the number of databases by 50. So if I've got 3 databases that ASM instance is running on, supporting, I would multiply that by 50, so that would be 150, plus another 50. So that would then give you the basis, if you wish, for the number of processes that you should be supporting. In fact, it's not another 50, it's another 250. The other metric we perform is if you're running more than 10 databases that are using that ASM instance, then you would multiply the number of databases by 4, and then add multiply that number of databases by 10, I should say, and then add 450 to that number. So you would end up with, say, we've got 10 databases, multiply that by 10, it's 100, plus 450, you'd have 550 processes set up in that database. So it's nothing special. A lot of databases are running with the default of 2,000 processes anyway, but if it's something that you become constrained by, that's something you may want to look at. There's another parameter called ASM disk string. Our recommendation is you try and set that to as low a path as possible. And what that is that's the storage mapping, so it might be /dev, /sd0, sd1, etc. You don't want to set it up at /dev because that just makes discovery processes slower, which is going to impact potentially mounting a database, etc. So that's another best practice. It's also advisable to limit the number of disk groups. So one thing we do with ASM is when we define how we store that data, we define these disk groups. And you can see here we've got one called data, FRA for flash recovery area, and grid, which is for our clusterware components. We recommend that, first of all, when mapping these disk groups, you assign a similar disk type. So in the case of having the Ultra SSDs or the HDs or the whatever set of storage you're going to use, you want the disk group to map to the same storage type. Because remember, it's striping and mirroring everything, and it's only going to be as fast as the slowest moving part. The next thing to keep in mind is that there are certain operations that we do for you under the covers. When we understand it's a flash recovery area, for example, we change the segments or the I/O sizes, the chunks that we write to disk for redo, for control files, for those types of operations. The other thing to keep in mind, treat those failure groups different. So we also create a level of redundancy with ASM. And I'll show you in our example there how the redundancy has been set up. But treat the failure groups differently for that level of redundancy for different objects. Can your database run without the archive log files? Absolutely, right? Do you need to impact the performance of your database because of the writing of those archive log files? Probably not. The other thing to keep in mind, the disks per disk group. So there's a maximum of 1,000. What you want to do is map that number of disks through the multipath or through multipathing, multiply that by, say, a minimum of 2. And then because you've got redundancy set up, you'll typically see a minimum of 4. So 2 disks for a specific disk group because you've got the mirroring. And then you've got the multipathing set up, so you'd see 4 to a maximum of 1,000. The other thing to keep in mind, allocation unit. Allocation unit is, when it first came out, was set at a default of 1 megabytes. Now we set that up to 4 megabytes. The allocation unit is the stripe that we lay the data across the disk, and it's very different to the block sizes. Fault tolerance. I already talked about that. One last thing, power limit. So the power limit is how aggressively we determine when we're going to balance the data across the disks. Do we impact the performance of the operations that are taking place on the system right now? Or do we have an impact? Do we say that rebalancing and restriping the data across those disks is more important? That's where you use the power limit. It goes from 0 to turn it off to 1024 to say balancing is more important. So thank you very much, Vaibhava. Do I have enough time for a demo, or have I run out?
I can show something quick.
OK, well, I'll show you something really quick here. So ASM, just so you know, let me set this on 7. So as I mentioned, ASM is an instance, and if you're running ASM, you'll see, I've got to get my context correct. If you do a ps-ef in your Unix session, you'll see there's an instance there. We've got an ASM plus ASM, which is the ASM instance, and we've got a database here. So I am going to do a .renv, and that will set my environment to be plus ASM. So I'm now going into the ASM instance. At this point, I can run the ASM command tool, and I can see what disks are there. Disk groups. So here we can see we've only got one disk group set up. It's mapped as external, which is mounted as external, which means we're not setting up any redundancy here. So ASM out of the box default is mirroring 2 copies. You can do high, which is 3 copies, or external, where you say, hey, the storage I'm running on is extremely resilient. Perhaps I'm running on RAID under the covers. I don't need to set up any redundancy. So that's one thing I wanted to show you. The other thing I wanted to show you, and forgive the setup here. This is something that was set up for us. So I just need to get in there. Oh, good, I got my typing right. So I'm just logging into the regular database instance that's running, and you'll see it's only a 12.1 database. Here I'm showing you the power limit. Honestly, you would want to set that within the ASM instance. It's an initialization parameter. And here I'm going to show you the disk stats for the disks that have been defined. Remember I mentioned data. We can see that it's under dev Oracle ASM disks data. We can see that it's online. The caching is implemented, etc. The next thing I'll show you, IO stats. And IO stats is just showing us the stripe. In fact, the previous one showed us the stripe size there. We could see the stripe size was defined. And then this one here is showing us just the blocks that are being written. You can see this machine's doing nothing, basically. But the point I want to make is ASM is kind of like a black box. The database is where you query everything through where you manage everything, etc. So that's it for me, Vaibhava.
Thank you very much. That was extremely informative. Thank you very much. This is great.
Thank you.
Wasn't that awesome? One quick thing that Sean wanted to talk about. Do you want to take a moment and quickly talk about it?
Yeah, we'll talk about that.
Yeah?
Sorry about that. I forgot that I had a slide after the demo. So really quickly, first thing that we announced at OpenWorld, actually, Oracle's OpenWorld conference, is we've introduced a direct interconnect using express routing from Azure and fast connect from Oracle to give you a 100 gigabit pipe between both clouds. So you can run your .NET apps potentially in Azure and your Oracle database in Oracle Cloud. We have the autonomous database that's running on Exadata, and it does ASM under the covers for you, so all of that functionality is available without you having to do anything. The other thing, we have a unified identity access model. So Active Directory works natively into the Oracle Cloud objects, into the database. Authorization and authentication is defined in the Azure space, and it works natively with the Oracle Cloud. Last thing, we have collaborative support. So if you're running your apps in Azure against an Oracle database in Oracle Public Cloud, and you hit a problem with your app, you contact Microsoft, and if they find out it's an Oracle issue, they'll work behind the scenes with our support organization. Vice versa, you're having a problem with the database that's using a .NET app, they find that there's something in Azure that's the issue, Oracle support will work at the back end there. So thank you.
It's very cool. Yeah, thank you very much for sharing a bit about that. It's definitely going to be awesome for users of both clouds. So we're going to switch to another workload. So we're going to talk a little bit about MariaDB, which is a fork off of MySQL. So MariaDB is an open source database. It is extremely popular. We actually have a ton of customers asking us about it. And so we have shared some best practices that we have seen has worked really well. Now, along with sort of the core tips and tricks that I shared earlier, what's really happening is that MariaDB itself has a set of defaults that come with the database. Now, if you're actually deploying extremely powerful disks behind the scenes, you want to use them to the best ability possible. And so some of those defaults don't actually match up. They don't actually enable the workload to run efficiently. And so an example of that is when you use direct I/O versus buffered I/O. Direct I/O actually means that you're writing directly to the disk. Buffered I/O means you're writing to a buffer that is in memory and then trying to write to the disk. This really, in many cases, conflicts with the actual MariaDB application and doesn't give you the best performance possible. So what we're going to do next is we are going to take a look at a demo to see how to see some very simple changes that can actually give you some strong performance improvements. So here I have a MariaDB server that is installed. And this is backed by the 3 data disks. So we have 3 data disks, which is an Azure Disk. One is for the data files, one is for the log files, and one is for the tempDB. And I also have a MariaDB client that I'm going to use to actually pass I/O into this database. So the first thing that we're going to do is we are going to start up IOstat on this server just to kind of see what is going on. So first of all, you see that nothing's really happening here. There's not really much I/O actually passing into this database right now because we're not passing anything in there. So what we're going to do is switch to the MariaDB client. And now we are going to do an OLTP write-heavy. We're going to start up a workload that is going to now hit the server. Now, what you see here is you see that you are getting some amount of TPS and QPS. It's sort of wavering up and down, somewhere around 1,000 QPS from 500 to about 1,000. That's OK. And then we look at the server, and we see here that I'm getting about 1,500 IOPS maybe on this server across read and write. We know that the disk is capable of a lot more, so that's definitely not the maximum we can get. So what we do here is we stop this application, and I have another window open for the server itself. And what I'm going to do here is I'm actually going to go into the configuration file for MariaDB to take a look at what is happening. So here I see the MariaDB database configuration file, and here I notice that this is actually set up with fsync, which is the equivalent of a buffered I/O. So what I'm going to do here is I'm going to change that, and I will make that O direct, which means that that is a direct I/O to the disk. And I'm also going to turn off double writes. What double writes or double buffering does is that if you're using buffered I/O, it actually writes multiple times to ensure that there's increased reliability. Now, because we're actually writing to the disk, and that is persistent and it's durable, we don't really need that. So I'm going to save that, exit from here, and then I am going to actually restart MariaDB. So it takes up these changes. So there, I restart MariaDB. And now, in a couple of seconds, this should come back up. And what we'll do is we'll switch back over to the client, and we'll rerun that workload that we were just running. So again, same thing, the OLTP write-heavy workload. And now, off the bat, we see that the number of transactions and queries doubled from what we were seeing earlier, right? Do you see that? Yes? Good? OK, so then we look at the server, and this is what we see. That, again, the read and write IOPS that you see here is double of what you were seeing. Right? Isn't that great? This is absolutely now maximizing the disk, as well as giving us additional queries. The thing I'm going to do last is I'm going to show you that even though I've changed these settings, and if I have potentially a mixed read and write workload, you will see improvements as well. So here, I am going to now run an OLTP read-heavy workload. This has about 70% reads and about 30% writes. And when I start that up, there, you automatically see that the queries are significantly high. This is great. As well as when we look at the actual server, you're seeing that this is really now maximizing the IOPS on the server across. And you see more reads than writes because that is what we're actually passing in as part of the workload. Right? Isn't that great? OK. Very cool, MariaDB. So if you have additional questions on MariaDB, or if you're using that as part of your application, we'd love to chat. We just saw that. With that, I'm going to switch to NoSQL databases for our next segment. With that, I will invite up Charlie from MongoDB to talk a little bit about their great application, which is called Atlas.
Thank you, Vaibhava. Hi, everyone. My name is Charlie Little. I'm part of our solution architecture team, and I'm actually based here out of Tampa. So I actually Ubered in this morning just to not have to drive over here. Let's see if we can get going here. First thing I want to ask is, anybody out there using MongoDB today? A couple of people. Anybody have experience, played with Mongo, or used it on an application before? Great. What I really want to focus on in the 5 to 7 minutes we have here is how MongoDB has a database as a service, which takes all the pain away of installing clustered and distributed databases and allows you to focus on getting your apps built and getting your apps up and running, has best practices built in. We're going to focus on that. But I would say up front that before I go into that, if you're running your own MongoDB in Azure, the best practices we just talked about that Vaibhava and Sean brought up are similar to what you would do if you're rolling your own. You separate your index file system from your data file system, and if you have some temp files going on, you can put them in higher speed areas, like the log file handling. So that kind of best practices apply to a lot of environments. Now, what's nice about the Atlas database as a service is you don't have to worry about that level of tweaking. It has best practices built in, and what it does is provide you an easy point-and-click way to configure your MongoDB clusters, whether it's a global deployment or just a single cluster in a single Azure region. It covers all the 29 or so regions that we have support for in Azure now, and that will continue to grow as our partnership with Microsoft continues to expand. And it allows you to set up read and write optimizations for where you deploy those clusters, and I'll show you a quick demo of that in a minute. Okay, so security is built in out of the box, so everything is locked down pretty much, so you're not going to make a mistake and deploy a cluster, put some data on it, and forget that you didn't set the security parameters correct, any of that. It also has comprehensive monitoring. So the cloud environments in general have nice tooling for watching your resource environments, but they're very generic to what's going on underneath the covers. So when you're looking at a MongoDB environment on Atlas, you're really looking at, what do I want to know about replication? What do I want to know about my hit rate on indexes versus scanning the document collections? Also backups. Backups in a distributed environment with a lot of data can be very difficult to manage. So having to not worry about that and using the cloud provider capabilities of Azure to keep those backups handled for you and just set the schedule for it and do a easy point-and-click mounting of a backup image so you can examine it and then kick off a restore process, and being able to do that without any downtime of the application environment. And then finally, if you want to build a microservices-based architecture and have some serverless functions similar to Azure functions, but do it in the MongoDB environment, we have the Stitch serverless platform that allows you to write some Node JS type of logic that is integrated directly to your MongoDB cluster, so you can call and provide microservices and a REST-based interface to your data access layer for MongoDB. Okay, so I mentioned there's worldwide or global coverage for supporting Azure, but importantly for everyone here, for those who haven't had a chance to play with MongoDB, Atlas provides free tiers that you just put in your email address. It doesn't ask you for really anything else, and you can run in Virginia or Europe or Asia for the free tier, and it provides a lot of guidance and educational support for learning how to use MongoDB, and especially getting the Atlas service to set you up a cluster in just a couple clicks. Okay, I want to show you Atlas real quick as a demonstration, and there's a magic button down here somewhere.
7.
Number 7. That work? Oh, 7. There we go. All right, let's see. Okay, so the Atlas service is just cloud.mongodb.com or atlas.mongodb.com. They'll both get you there. And if you have a new account, it'll kind of start off with a quick walkthrough, but I already have one set up. And what we're going to do is look at a cluster and what can I do with setting up a cluster, and what is it providing me for parameters to make sure I get good performance out of my environment. And then I'm going to go into a few details about what we're doing behind the scenes with the Azure Disk subsystems as far as choosing best practices for getting good performance out of MongoDB. So I choose which region I'm going to set up for, and if I select the multi-region down here, I'm allowed to split it up and have a cluster spread out across multiple regions. One highlight here is anything with a star next to it would be preferred regions where you have multiple or 3 fault domains. So that way we can put each member of a 3-member cluster set, high availability set, in individual fault domains so that power and racking and all that are independent. So if you did lose some hardware infrastructure in a part of an Azure data center, you still have the rest of your cluster available without any impact there. Okay. Then the tiering is how big of a database cluster do I think I need to start with. Again, the M0 is the free sandbox, so you can play with that anytime you want. But if you're going to think about a large test environment or a production environment, you're really going to go to one of the M30 or larger tiers. Okay? And we go up to M200. And when you select a tier, let me go to a slightly higher tier. Let's say we're talking about performance here. We're talking about serious workloads. So let's go with a 64 gig memory footprint available for this node. And the whole cluster is going to be 3 replicas of this size of virtual machine, 128 gig of disk space by default, but really you're going to be able to ramp that up. Disk is always auto-scaling. You can turn it off if you want to, but auto-scaling for the disk just means that I don't have to worry about disk space. I start with what's reasonable, and if my data growth continues at pace, I don't have to go in and manage that at all, up to a limit of 4 terabytes. And as you see, as I'm adjusting the disk size here, we're calculating the IOPS based on the disk subsystems we're allocating from Azure, and it's going to be multiple disks applied to the larger sets, or at least the higher grade IOP disks are actually applied. And so I can get up to 7,500 IOPS per second for a single cluster member. If I want to also scale up memory and CPU, because MongoDB, even with fast SSD, even if we were using UltraDisk behind the scenes, memory, random access memory is still much faster, right? And it's closer to the CPUs anyway. So combination of CPU and memory is what MongoDB tries to optimize with the WiredTiger storage engine that we're using underneath the database process. So WiredTiger likes to minimize I/O by having compressed information, compressed data off the disk, pulled into memory, and then doing checkpointing and journaling to minimize I/O back and forth, and using as big a cache as we can take from the memory footprint of that VM. So in a 64 gigabyte machine, there might be 32 gig of just cache used, so we can get as much of your indexes and your working set into memory as possible. And that's where you're going to get the best performance overall. Okay, one newer feature, which is really makes life easier as far as scaling, is the ability to auto-scale up and down your VM tiers without having to go in and manually manage it. Now, if you have predictable loads, you might as well go, oh, well, I need to go up to an M200 for my Black Friday event, and then I'm going to scale it back down to an M60. If it's predictable, then you can easily manage it yourself. All this, by the way, is available through an API just as well as the user interface I'm showing you here. So if I want to let that auto scale, what it's going to do is going to watch your CPU and your memory usage. And after an hour of continuous high watermark usage, it's going to auto scale it up the tiers that you allocate or that you specify here in the, we're going to run short of time. Okay, here in the user interface. So that's just some of the highlights. I want to go back to the summary features of what we're doing for the Azure Disk subsystem. We start with premium disk for everything, and that gives us guaranteed capacity and IOPS, and also allows us to do predictable snapshotting of the information on the premium disks. And it's also available in all the regions that we support. UltraDisk will be coming in the future as appropriate. And then finally, backups are done using Azure Blob Storage, and you could actually download your backup images and use the archival capabilities of the Blob Storage environment. So thank you for the time, and thank you, Bhavana.
Thanks so much, Charlie. That was super useful. And we hope all of you go home and try out Atlas in the free tier, as Charlie called out. So I actually had a cool Cassandra DB demo, but I have 13 seconds, so I don't think that's going to happen. But we will share the slides out. And what I can also do is share that link with you, which has some great best practices around Cassandra DB, if that's something that you're trying to do. This really talks about how to optimize both the in-memory as well as disk writes. So definitely go check that out. And then really, these are our key concepts and tricks for you to go try out at home once you head out. So thank you once again for being here this morning and for joining us on a Friday. This has been really fun. We'll stick around to answer any questions. These are some of the other disk sessions. But thank you very much for being here.